Thank you so much. Let's invite someone else. He's up here or down here. Come up. Alan Rowan, ladies and gentlemen. Alan is with the Division of Molecular Materials at Radboud University in Nijmegen.
A little bit this way.
You need sunglasses?
Yeah, so something like that.
Okay.
Yes.
Anyone with sunglasses?
No, it's okay. I can
Perhaps we can fill them up by some technology. I don't know. Anyway, we asked Alan to come here and discuss the one part which I think intrigues us all, and that is the feasibility of this. I can understand the principal possibilities of this atomically precise manufacturing, but what is feasible? Your first impressions of what Eric Drexler is telling us?
Well, I mean, the first thing is I'm not completely against nanotechnology. We may argue a little bit about the definition of nanotechnology, and I clearly see that if we could do what you suggested, then it would have dramatic effects. In a cynical way, I sort of was listening to your talk, I sort of imagined Leonardo da Vinci drawing the picture of the bird and then trying to discuss the problems of mass transport, because the point is we're sort of so far partly away from what you're aiming for at the moment that maybe we're discussing some problems which I think we could argue that, which are not necessary at the moment. But I do think we're on a track in the long term to something like that. There is, I think you made also a comment, it's just in the molecular detail, but it is in the molecular detail, and that I don't think we're anywhere near yet. I certainly can't see it in how we do it, getting to this atomic precision delivery.
What problems do you have in mind more specifically?
Well, the fact is that people have been doing self-assembly and bottom-up approach for 20 years, and self-assembling molecules into structures. What we realize, we're really in the infancy of it all. We have a long, long way to go. And then when we try and talk about atom assembly, when you talk about your little rotors and motors where you showed you could just put, that to me becomes exceptionally difficult simply because we're in the realms of Brownian motion. Putting one atom on top of another atom is not trivial.
Okay, let's stop there. About these rotors and gears, etc.
Yes.
They look very nice on these moving GIF files, of course. But can they be built?
No.
No. What are we doing here?
So why do you leave?
Today.
Okay,
Today they're absolutely impossible. And if you take a short-term perspective asking what can we do in the laboratory, the answer is you can't do that. Okay. And if you assume that people who are discussing these things are, as most people are, talking about things they think you can do, then no. You think the discussion is off track.
No, but I mean, you have to also be realistic. That's a bit unfair to say that. I think the point is that I think most people here would say, well, they're not disregarding a vision you would have if I suddenly made a wonderful solar cell. But in your mind, what timeline are you looking at in this? I mean, is it 30 years or 100 years? I mean, given that you sit and study this, what would you say would be a realistic timeline for this?
That is, again, a question that crosses over into speculation. We can describe the physics and chemistry very well because it's a matter of physics and chemistry and engineering.
Absolutely.
What one cannot predict is how long it will take people to address problems and to solve problems which, particularly along the pathway of the technology, are more difficult to understand, more difficult to analyze than the longer term for technical reasons that I'm sure you're familiar with in molecular modeling and the complexity of dealing with soft matter systems. What I tend to say is simply that, in my view, 10 years is a short time, and 20 years, I think, is a long time with respect to these technologies.
Okay, show us your face. 10 years short, 20 is long.
I've been in chemistry for 30 years, and that seems a very short time, so I'm not so sure if 20 years is really doable. I think we're looking at a much longer period to get to that idea of that sort of real molecular control on building things, bringing things in, putting them in the way we're at. I think it's far more complex than maybe you suggest, and what we realize ourselves is that as we try and do this, and again, I project what we're simply realizing what we don't know, so I would say...
Here's a question. Considering the range of areas where science invests attention and engineers are working on developments that might have some application to global problems, would you say that this line of development is one that might be interesting, but we shouldn't be doing anything?
No.
Or perhaps I'm not trying to put words in your mouth.
No.
Or possibly a rather high priority to understand better, to explore to explore what can be done and to pursue what that exploration shows us can be done.
But I think we're doing that anyway, but not quite in the manner you described.
Not focused.
Well, I disagree. In that not focused in a direction you think it should go in.
Not well. I'm proposing a direction, and either the focus is in this direction or it's not.
No. But what I would say is, what I would argue is that we are using in a different, maybe a slightly broader term of nanotechnology. What we have now, what has enabled us to go further, is the ability to see at the nano level. You would agree that more recently, certainly in the last 10 or 15 years, the biggest breakthrough is we have now the technology to see at the atomic level, to see in the nano regime. And what that has enabled us to do, which is partly on the way you're talking about, enables us to self-assemble and look at materials and say, well, listen, this is its properties, but now I can zoom in and see how it's nano-assembled. Let's go back to the lab, let's then try and change how it's assembled, or see, well, actually what happens is we go and play with something and look again and say, well, it's slightly different now. So how does the nano-architecture affect the properties? That's the first step. So we're like little infants stepping on those lines. And that's making bigger inroads into solar cells, into osmotic filters, as you mentioned, and in those sort of directions.
The major topic that I discuss in the book is the difference between a scientific approach to a field and an engineering approach.
That's right, yes.
Okay, perhaps you can expand on that, yes.
Scientists focus on what is not known. Engineers look for what is known and sufficiently predictable that a modest number of experiments will make it work, and they ask, what can we do with those things? Much of semiconductor physics is not thoroughly known. On the other hand, the semiconductor physics required to build computer chips has been thoroughly studied, and people are building on known ground. Molecular self-assembly. Many areas it's very hard to design and predict. But in structural DNA nanotechnology, 1 million atom structures can be designed in a day and fabricated as soon as the couriers deliver the oligos to you for the assembly.
Yeah.
Routinely, it's like carpentry.
Yeah, but the two are not mutually exclusive. I think in your book, what has happened is that the science comes first. I completely agree with you.
Yes.
And then basically they try and use, the engineers may take some of that, but we've not got the science done yet. I think that's the problem. We're quite a long way. The engineers don't have anything to actually build at the moment because we haven't got that.
We don't have the engineers because the knowledge, scientists have the knowledge, engineers have the methodology, and what we don't have is a community of macromolecular systems engineers. We have the components, we have the science, we do not have the people who are looking at this set of tools and very systematically asking, how can we avoid problems as much as possible? What problems do we need to solve, and what can we put together? What can we accomplish in system building? It's not there.
Let's ask the scientists, though, like Alan Rowan. What exactly is recognizable from what Eric is sketching out in the lab today? What can we do? Or what can you do?
Well, I mean, some of the terminology, the idea of molecular assembly, the idea of bottom-up approach has been around for a while. The next step to actually building machines where we can sort of build gears and so forth, etc. Well, we sort of play with little things. We're nowhere near the sort of rotors or motors or anything like that you possibly discuss because we can't handle atoms and molecules in that level. And the idea of the 3D printer scaling down to a simple, I find fanciful in that context. So that I can't...
What concept?
Well, when you sort of put the image up of a 3D printer that we can 3D print atoms on top of each other or molecules. Well, no, you may not intentionally do that.
Not atoms putting in place. That's a fantasy.
The concept of just printing molecules on top of each other, we're not yet there. Because again, of this problem of controlling that, which we are in the process of learning.
Yes, it's a process of using tools to build better tools. And I have not described the pathway. It turns out that one of the most critical needs is for controllable stepper motors.
What do we need?
Controllable, reversible stepper motors.
Which is?
Well, in a printer, how does a printhead go from point A to point B?
Okay.
Well, there's a little motor in there that goes step, 35 times, and here you are. If you had a molecular configuration, people have already made motors, and you see interesting things in biology, where you could have a signal input and have a device that goes step over here, and back, 5, 10, step. If you have 3 of those on 3 axes, you have 3-dimensional control, and you could position a tool.
But you need something on the atomic or molecular scale?
100 nanometer scale, like the DNA, structural DNA systems, but different materials.
Okay.
Can be done by self-assembly.
Getting quite nervous now.
No. I think that you use the analogy to to nature, you mentioned a comment that where you talked about this is a sort of thing. I think nature gives us many examples, particularly in how it builds machines inside a cell, for example, of replication. And I do think that the current technology, or certainly the way the science is going, is trying to understand how all of this works much more. We have the skills now to cut and paste, as it were, in nature, so we can try and start to understand how these motors, understand how to position things like that. And indeed, we're slowly making steps for this. I think it has to come back to your 15 years, I think, is very much on the short side. I would think of maybe 50 years would be a far more realistic point about really what we're going here, because it's far more complicated than you give it credit for.
Biology is far more complicated, but we did not build jet aircraft by cutting and pasting birds.
Yes, but we're not talking about building something which is macroscopic. We're talking about being down at the nano level where
You don't build small aircraft by cutting and pasting birds
You don't build nanoscale aircraft. It's not the same. I don't think you can do that simple analogy. You're just going down in size and it just scales easily. That's where it becomes difficult, because
I can build that analogy.
I can build a motor because I can have somebody, I can see it and I can stick it together. When I'm trying to deal with something which is thousands or tens of thousands of times the size of a human hair and cut and paste and put them down, that is when it becomes difficult. That is not a trivial thing to say, well, listen, I could just do this.
Yeah, what I find difficult is having a body of technical proposals and having a discussion which sort of sets at a distance and says, well, you might be talking about doing this, or you might be talking about doing that. And if you were talking about doing that, that would be foolish. And if you were talking about that, it would be foolish. And a number of the pictures that you've painted, the word pictures that you've painted of ways in which one might try to move forward, and then you've said that doesn't make sense. I agree with you. The pathways that do make sense are ones that come out of very careful selection of approaches.
I think we've lost you. The nanotechnology's got to you yet, yeah?
There are many more systems that don't work than do, and finding the ones that do is a matter of careful engineering. Is a matter of careful investigation and problem solving. And a pattern that I've seen over the years, Richard Smalley did this, was he said, I can think of something that won't work.
No.
Well,
Let's not get into this is not a fair debate. I mean, the point I'm trying to say is that what we're doing is we're presenting the public of where we think nanotechnology is going to do. And without doubt, if we could achieve everything we would like to on our wish list, it will have dramatic changes for society. I have little doubt about that. I do think that the solving the problems doesn't necessarily require this atomic molecular precision technology you require to solve many of the problems you put up there. We can do that by just using some of the ability to see at the nano level to make things better and more efficient. I think the two
many applications of nanotechnology, I quite agree.
Okay, so it's not just that one.
Isn't one of the problems I sense in this discussion, like in many discussions, that somehow your vision of nanotechnology or atomically precise manufacturing is somewhat mechanistic? And on the other hand, you have chemistry and biology and all this goo going on.
Weird goo, huh?
Yes.
It's messy.
So isn't the real problem that your visions are somehow like Lego or whatever play systems you have, whilst on the other hand, in the lab, materials tend to be something far more
dynamic and flexible.
Dynamic. Isn't that the whole point?
Yes, dynamic and flexible materials are dynamic and flexible, and rigid materials are rigid.
Right.
And what we can make today are, with precision, are dynamic and flexible structures. Where we can go in the longer term is rigid and predictable structures. So part of what people find very confusing about this is that the advanced technologies, the ones that are not accessible yet, are easy to understand, easy to model. They're a very tractable medium for design. The path there, however, leads through, for example, protein engineering. And I published the paper that was the founding paper in the field of protein engineering. So I have the 1981 Proceedings of the U.S. National Academy of Sciences. So I do have some background in thinking about soft matter and design. In that paper, I drew a distinction between the scientific problem of predicting what nature does and the engineering problem of designing, with the same materials, a predictable structure. And the result was that people in the field who thought they had to solve the first problem said, oh, those are different problems. and now we have many journals of protein engineering, conferences.
But we still haven't solved the problem exactly.
We have solved enough problems that people routinely use the Rosetta design software to design structures that fold predictably. It is a field of engineering.
It is, but it is. But I would not disagree, and I do think that science is going that way, in that what we do miss is having communities, not just a science. So this idea of having a team focusing on a problem, where you might have maybe even sociologists for a complex problem and an engineer is the way to go. I do think that with this ivory towers before of just the individual sciences is definitely going anyway.
Okay.
And that if we get there, that is indeed. But you will find that a lot of material scientists also are thinking into the material aspect as a final engineering problem as well. It's not just something they dismiss.
Yes. In terms of the direction that organization has to go, I agree with you. I agree entirely. Yes.
Yeah.
Very important.
But also in the shorter term, I also think that nanotechnology probably will have a far more impact in nanomedicine initially, in the shorter term, than it will have in these problems. I do think that the technology there is far more amenable to people. So there's a stepping stone, and,
yes.
I think it's a far longer picture than maybe we could debate that, and we are.
So you mentioned nanomedicine.
I think we're in agreement on that.
Is nanomedicine in your book, for instance?
I don't discuss it much, but I briefly point out what Alan just pointed out, which is that it's enormously important and it's a leading edge in these areas.
Let's define it, nanomedicine. We've seen many images of tiny molecular robots floating along our bloodstreams, etc., etc.
Yeah, this I equally agree with Eric on this point. This does me no good.
That's not what we meant by nanomedicine, I guess.
No, not at all.
Okay,
Quite
but
so.
what do we mean with the word nanomedicine?
Well, a lot of nanomedicine today is about putting together molecules and small particles to make what amount to drugs, but are larger than molecules. They're particles that can move through the body that will have certain parts that bind to a cell, other parts that do something, multifunctional.
Okay.
And parts of those structures are atomically precise, as
But
much of biology
that's
is,
not
and
something
parts
we
aren't.
would call chemistry, for instance?
It uses chemistry.
Yeah, it's
Okay.
biochemistry. I mean, this picture here, I mean, I must be honest, I could say I just had a patent last week submitted where we do basically this on nothing which looks like a robot. But what we will make is a polymer which will go around your body and it will bind to a cell and, as you rightly say, recognize it and trigger it and carry an event.
Okay.
And that it would be a nanotechnology, but it has nothing to do.
Why exactly is that called nanotechnology then?
Well, this is we debate because the actual the size of the actual polymer is stiff and it's only nanometers in dimensions and it's so many nanometers long, and that it helps it get through the body and around
When
the
you
body.
say that might be a stepping stone, is there anything in there leading to what Eric Drexler is seeing for the,
Well,
the
first
far
is that
future?
I think public will be far more comfortable with nanoscience and nanotechnology as they see it be more beneficial. I do think that will play a role, and that is a very important
And
point.
do you agree it might be a stepping stone towards further developments?
It's one of many areas that is exercising, extending, providing motivations for improving the ability to do atomically precise fabrication of functional systems.
Okay.
And that's a broad frontier with many applications being driven forward in part by nanomedicine.
Okay. Well, you've come somewhat closer, I guess.
Except maybe
we're
a
quite close.
timeline.
One question for the audience at this particular point. Anyone? Yep. Oh, I'm sorry, only one.
It's actually a question for Alan Rowan. When you say that the analogy breaks down when you go to the molecular level and the atomic level, does it break down in principle, or does it break down because of technological progress?
Well, I think the problem is that I can add one molecule to another molecule to a molecule and sort of grow a peptide chain out on a bead. But that's more a bulk solution where we just bash molecules into each other and statistically something happens. It becomes much harder when I want to actually take a molecule and push it in the right direction and make that bond and try and get it precisely to do that. And the problem I see foreseeing is how to control this, how to be able to manipulate and control this, given that molecules themselves have so much motion. Unless they go down.
Alan, What people need to understand is that this is not some ideas, well, maybe we could do so-and-so. There's a body of technical analysis here that looks at the Boltzmann distribution of thermal energies, looks at the mechanical restraining forces, asks what is the variance in position, what is the error rate associated with bringing molecules together, calculates that out and says, this physical system can do that.
No, but I'm not disagreeing that if you took all the numbers in. I'm just trying to say I find it extremely difficult to see how you're going to do that. I mean, I could predict
Through many
maybe
intermediate steps.
Exactly,
Yes.
in many. I mean, I could say that
immediately.
if I could do this and this and this, maybe in 100 years I'd have that.
Well,
but I
the
mean, what
dates
I'm trying to say is I find it very difficult to understand at the moment, and maybe you're quite right. In X number of years, something will. How to actually control that is extremely difficult.
Okay.
Extremely difficult.
It's a matter of progressive development of tools.
As is everything. Yes.
Like I said, he's the optimist.
No, I don't see there's a problem.
Okay, let's leave it to this. Thank you, Alan Rowan.
Thank you.
The second part you talked about was about the possibilities and the way these technologies could change the world, etc. We asked Tsjalling Swierstra to join you in the discussions right now. He's at the Department of Philosophy of Technologies, or New Technologies. What's the exact word? Emerging Technologies at Maastricht University. Tsjalling, take a seat. Well, gentlemen, if it could be done, what world would we end up with? Tsjalling, what's your first impression?
Well, I was listening to Alan and I thought, well, the basic approach of Alan is this is too good to be true, whereas my doubts are more this is too good to be good. When I read the book, I found there's lots to like, and I think Eric says he has two aims. Well, he says he doesn't aim to convince, but he aims to raise urgent questions, and I think he succeeded excellently on both accounts as far as I'm concerned, because I'm not really convinced, but I do have a lot of questions. The major thing that I would like to talk about is whether this is an engineer's fantasy to solve the world's problems. And it's interesting how you, in your autobiography, you describe yourself as someone who says, I'm really going for vision, wild vision, but it has to be harnessed to physics. It has to be grounded in reality. And I thought maybe it has to be harnessed to social science and hard-nosed humanities too, because we know something about how society works, how human beings interact and are, and it would be very interesting to explore further on how this technological revolution would affect us, and vice versa, how we could affect this technological revolution. Because what I really hate about the book is the subtitle, how this revolution will change your life. That's a kind of, that it's written in the stars that this will happen, whereas the book itself argues that a lot has to happen if we want this to happen. So we are here together in a conversation deciding what we want to happen, how we want it to happen. And the book actually ends with that call for a conversation, but somehow it's still in this let's say, a bit old-fashioned gear or groove of this is going to happen. And I think it's not completely balanced in the book. So at least I'm pretty sure Eric's better self thinks this is not going to happen, the subtitle is wrong, it may happen if we want to.
Subtitles are negotiated, not written.
Okay.
It obviously raises the question, do we want this to happen?
Yes.
So, what do you think?
I'm thinking it's a radical experiment. Let's imagine a world without scarcity. And we don't know what that is. You could say that economics, politics, ethics, they're all predicated on the basic line, you can't always get what you want. The Rolling Stones were right. Somehow, this book turns this into abundance. So now imagine a world where you can always get what you want. How would that affect I completely agree with you that we don't have morals, politics, etc. written in stone, but we have to think how deeply shaken we would be, ethically, politically, culturally, economically, if you could always get what you want. Imagine how many people are having diamonds on at the moment.
Okay. Who's wearing diamonds?
Raise your diamonds. Well,
One.
Okay, that's
Two.
one. It's Amsterdam, so don't raise them too high. But the whole idea of a diamond is that they're scarce. That not everyone has one. And so I think there's a lot of things in our life where scarcity is a condition for meaning. You don't want your partner to be abundantly available to everyone. Some things we want to exclude others from. It's interesting if you look at abundance. I think the best model for what Eric is driving at is the information revolution. And he says, well, now we have an abundance of information, and I completely agree. But now people are paying good money to reduce this abundance of information because they have information stress. So we will have new problems to deal with. Also, he says, well, basically he's describing factories where humans don't have no role. He says, agriculture, well, we have to intervene a little bit because there are all these pests and diseases, but in itself it would work. It's a perfect system of manufacturing without our help. Now, how would that affect us if we would no longer be manufacturing things? Of course, you can say, well, go write books, go listen to Mozart all day. But of course, we don't want to do that. Part of what gives our existence meaning is that we go to a factory, that we help produce things, and then also enjoy a sense of achievement from our labor. And well, I hope you start disagreeing someplace here, but it's this.
Sounds right to me.
We have to think, at least, how attached are we to manufacturing? Where would we get our sense of achievement from? How would we relate to material objects? For example, Eric gives a beautiful example of a new car produced, and it starts, for those of you who are Dutch, I can say this in Dutch, it's reversed Droste effect. Basically, it's not smaller boxes going into smaller boxes, going into smaller boxes, but the other way around. It's going from very small boxes, going through ever larger boxes. In 2 minutes you have a car, you drive it out of your garage, lo and behold, you see 6 cars standing there already because they don't cost anything, and so you drive 2 minutes further and you throw it away in the bin. So how would this affect our relations to the material world? If we could produce everything and throw everything away, would this make us more sustainable, really? Would it make us more... there's no engagement anymore with the things that we make or that we buy after having to... I think our whole psychology, moral economy will be disturbed, which is not necessarily wrong, because we have, let's say, technology is essentially something that disturbs us, that disrupts us. I've once defined modernity as that age of human history where we are every day disrupted by technology. So in that sense, there's nothing new that will happen again. But I think the question here also for our discussion now is, how are we going to organize societal debate and reflection and power to make sure that we get the technology that we want rather than the technology that seems to be written in the stars? And that's something that's touched upon in your book, but you say, well, that's more than I can have on my plate. It's also more than I have on my plate, but it makes me a little bit worried that there's this sense, well, we're moving ahead anyway, and then we hope that our children are there to mop up the pieces if necessary.
So you've raised quite a few questions by now. So perhaps you can try to find some answers from Eric Drexler. For instance, this radical abundance theme, there's no scarcity of goods or materials. So what would there be any economy left?
What would we lose?
Okay. No?
First, I would note that I don't think that manufacturing is that important. I mean, you have a box and it can make things. Well, okay, so you have things. It's not everything people want. People want much, much, much more than things, much different than things. In part, so-called positional goods, you were mentioning. Yes. What I aim to do in the book is to build from the science and engineering and physics up through questions of what can be provided that people clearly want and will strive for, and then ask, given that people will be striving for these things, what will happen or be stopped? What will happen unless it's stopped? Which is not a prediction. It's saying, here's a problem that arises and must be dealt with. My purpose is to lay a foundation for discussing the issues that you have so well described as the central, crucial human issues. The technology itself is not important. What's important is implications for people, and those implications are profound, complex, mixed. I'm far from enthusiastic about these technologies. They, physics and engineering says they're there. These are possibilities inherent in the natural world.
What you're saying is, hey, look at what this could mean to our lives.
And competitive pressures say, now we're stepping one step away from the engineering, but saying people consistently through history have pushed technologies forward. The direction toward atomic precision is a direction people have been moving for a long time. It's hard to imagine a world in which that doesn't continue. Either it will happen or it will be stopped. And in a competitive world where no one is in a position to put their foot on the brakes, can you stop developments in Japan and China? I can't. Can China stop
traditional means now.
Can China stop developments in the United States? I don't think so.
Right.
So competitive forces push forward. Where we go is another question.
Yeah. I think that's interesting because, let's say, 20 years ago, everyone would have agreed you can't stop progress. And because it's written in the stars, it's internal autonomous logic. And nowadays well, in Holland we say you can't stop the Belgians, because we may have moral qualms, but they certainly don't as Catholics. So there's always, because the others do it, we also have to do it. But that's basically a political dynamics. Now the interesting thing is that if I understood you correctly, you say we need scaling up of this scientific research. And I find that's interesting because you see this in several domains, this plea to scale up research. And this basically means that we have to say goodbye to this model of the inventor scientist working on his own, doing brilliant things, and it's much more large scale, almost army-like organization. You do this, you do that, and together we come back. Now,
it starts to sound like the Soviet Union in a certain period.
It's of course we want to have these brilliant people too, and so. But I think it's really a problem. There's a growing tension between, let's say, the romantic ideal of being a scientist, going for truth, and being brilliant, more brilliant than the rest, and this much more modest. Factory-like conception of science.
Drexler, the conception of a scientist might change also, is that correct?
Well, I think that the trends that you're pointing to are real. I think that they are problematic. There are some areas of science that require that approach. Applying that approach more broadly is bad. It's important that much of science retain its traditional curiosity-driven investigator nature. What I would say, however, is that there are areas of science that are ready to give birth to fields of engineering, and that engineering has to be organized differently. Scientists, if you have many groups of scientists that are going in all different directions, investigating different areas, well, that's great. It's good exploration. If you have small groups of engineers who are going in all different directions, they're never going to make parts that fit together to make an automobile.
Right.
So there's a fundamental difference between the kind of coordination that's necessary to architect systems, design subsystems, sub-subsystems, design the components, work out the details, integrate, test, and so on. It's fundamentally different from studying nature. And recognizing that and using the right kind of organization for the right tasks, I think is critical.
May I ask you a question? How do you think about, let's say, the scientist's responsibility? Yeah, because what you often see is that the scientist says, okay, there's a problem. What I always call there's a hole in reality. Let's plug technology in, and then reality is whole, and then we're fixed. And then, lo and behold, as you point out yourself, never works that way, because technology is never a passive tool. It's always an agent, an active shaping power, which always has unforeseen consequences. You have this beautiful example of how the invention of the automobile shaped the shape of American towns. And of teenage sex, because it's a researched fact that, let's say, the backbench of a car is for many American teenagers the first place to meet. So we have these unforeseen consequences. Now, is it enough as a scientist to say, okay, here I am, I hand over the tools somehow, and now it's up to society to do with it what it deems fit. There's this lovely quip, I think someone said, science takes credit for penicillin, society gets blamed for the bomb, Radboud. And then there's this nice thing, if things go right, it's science. If things go wrong, society made a mistake. And
I
somehow,
think one thing you can say about Eric Drexler's book and works is that he's trying to raise the point.
So I'm not accusing him, I'm inviting him to elaborate.
Okay.
So many different facets to elaborate from. Which one did you have in mind?
Do you think that in this time and age, scientists can still say, I'm only developing the tools, now it's up to society what it does with it?
I think that scientists are part of society. They are in a position to do things. They're in a position to bring some expertise to the process of judgment. They're not themselves in a special position of judging. Scientists should not be given more moral authority than anyone else, but they also have the same moral responsibility that others do. And more is required because of their position.
Mm-hmm, mm-hmm. But I also think that in practice it's not so easy to say, here I speak as a scientist on the facts and here as a citizen on the values. It's when you look at how technology and science evolve or are developed, if you go to a laboratory, there are constantly values involved, constantly discussions where where choices are made, where priorities are set. And somehow I think it would be nice if we could come up with kind of interdisciplinary research programs where, let's say, scientists from the natural scientists would closely collaborate with people from the humanities and social sciences to make sure that in your next book, the second half is as well researched as the first half. And the other thing is...
He's applying for a job, I guess.
Yes. The second half was intended to provide you with a job.
Yes. Thank you. And the other thing I think would be great if we could somehow engage, let's say, the citizens that are somehow the intended audience for all this technology, to let them have a say. And to somehow, if we are going to scale up this research, which I think is inevitable, then also we have to come up with institutions that make sure that science can check, can control, but can also help set priorities for what scientists and technologists do.
Yes. And I think that we need better institutions, better mechanisms for distilling useful, reliable knowledge out of science of forms that are applicable to public policy. At present, we see scientific debate being mixed with politics, being mixed with mass delusions on the internet. And I think that there are ways of structuring internet institutions, if you will, that could, through spontaneous social processes, bring forth a better picture, a more clear picture of the causality in the world, the facts about cause and effect that have to inform the relationship between our values and our actions.
I'm afraid it's getting a bit abstract right now. It is.
It is.
I was wondering, to end this discussion, which is not finished yet, of course, obviously, I had this question all day. Suppose you have this box of miracles.
Engineering.
Engineering. It's another word for miracles, isn't it? Suppose we have it. You have it. What would you like to get out of it first? The first thing to build like this?
I think that in the nature of the way that technologies unfold, and this one in particular, there will be no first application.
Now you're evading the question.
There will be a gradient of increasing capability and broad applications that we can't really predict. In terms of intermediate technologies, the first thing that I would want out is better tools for building the next generation of tools.
Okay, that's a good one.
And a focus on that path is, I think, what is more needed if one wants to pursue the forward direction here. A focus on how can we use tools to build better tools in the molecular domain is really central. Tools.
Tsjalling Swierstra, what would you like to get out of your box? I'm coming to you. So think.
Well, the first answer is nothing, because I feel I have everything I want. So that's the thing. Now, if let's say, if you ask for the world's problems to solve, and that's the level we are discussing, I'm a firm believer in women emancipation. I think that would solve a whole lot of connected problems in the world. So let's start with very cheap anticonceptives.
Okay, clear. Anticonceptives. Okay, who else? What do we need now from this box? Anyone?
Well, I was thinking about Douglas Adams' The Hitchhiking Guide to the Galaxy, and then was a problem because some machine would make was supposed to make nice tea, couldn't make nice tea. It was always the same mud or something like came out. So I would say, well, something like nice tea, nice coffee, etc.
Nice tea.
Food.
Okay, I think they've already designed these kinds of boxes. But yeah, take a look tomorrow. Okay. Who else? What do we need? Scream out. Come on. Pardon? Medicine. Okay. For a particular disease or just in general? Medicine. Way. Okay.
I think maybe some filters and stuff to remove the less technological, promises that we spread all over the world, like PVCs and asbestos and those kind of things.
Okay. Filters. Good. What else?
Grow products without machines.
Pardon?
Grow products without machines.
Grow products without machines. Like for instance, weeds or... Okay. Okay. Up there.
A universal Turing machine, well, probably nano Turing machine.
Doesn't that already exist? Perhaps it is. Yeah, right. We use it all the time. Anyone else? Okay. A language with less words. But that's information technology. It can be done already. Okay. Who else?
Could it also be something fun, like a perfect model airplane?
A what?
A perfect model airplane, like an airplane, I don't know, an Airbus, but exactly an Airbus, everything in it on it, only very tiny.
What would you use that for?
Okay,
For
also
fun.
remote. Yeah, fun.
Okay. Yes.
Something to sweep up cat hairs.
It's nearly there, I guess, but without you pushing it. Is that correct? Okay. Final three. Okay.
Something not for humans, so something for other species that we took so much away from already.
For instance.
For elephants.
Animals.
Yeah. For
Okay.
anything. Dolphins, elephants.
She likes the dodo back. Okay. Now we're getting started.
Providing more room for nature.
Providing more room for nature. How about money? No one?
Can already print it.
Pardon?
Can print it already, no problem.
We can print it already. Okay. Up there.
Would it be possible to fabricate a house on the moon using this technology? So we can explore and utilize space better.
Okay. You like to go to the moon? Okay. And afterwards to Mars or... Okay. Have fun. Last...
So we already live in a world of abundance. So I hear lots of people talking about things that are already there. So I think we should either look at the stuff that is more effective to get here. So that happens with 3D printers also. But the toolbox should be used for a more efficient production of tools. And then all sort of new things. So new technology, new stuff that we don't yet know of. This iPhone didn't exist 10 years ago. So, 10 years from now, there are all sorts of new products.
Okay, so something, but you don't know what. Okay.
But would you still be interested in all these new products? Well, are you one who is eagerly waiting for the iPhone 6, or do you say, well, I'm kind of losing my interest here?
Well, I disagree with about all you said previously. We already live in a world of abundance. Half of Amsterdam is not a production unit. So we are not looking, as human species, we don't look for being a production unit. Having said that, there are a world of new products that we can think of. But life is not about products. Maybe your life, not mine. But products make other things possible. So I can think of numerous of products that would help me to become a happier person.
Okay. Yeah, but they also make things impossible. I travel a lot by coach, and it strikes me that everyone is gazing at their... I don't have a smartphone. Everyone's glued to their smartphone. So let's say let's discuss new technologies. Always, what do they enable, and what do they make impossible?
What do they make impossible? Discussions in the train.
For example,
on the implications of technology,
staring blandly out of the window. That's also very...
Okay. I was just passing light to note, this is a stupid phone. And this is a wind-up mechanical watch.
Yes. So
okay.
Stupid phone.
What can I say?
Just show me yours.
No, I'm sorry. Sorry. I can only say the bar will be open afterwards, but before we go there, I'd like to thank Tsjalling Swierstra, of course. Thank you. And, of course, Eric Drexler. But before we really leave the room, we have the floor for Jelle Reumer, who's our columnist every month. And who'll be talking about nanotechnology right now. I guess you'll be talking Dutch, won't you?
Yes, I will.
Okay. Jelle Reumer.
Yes, it'll be in Dutch. Does this work? Yes. It'll be in Dutch. I already explained to Professor Drexler, and he fully agreed, because we are in the Netherlands. But it's also because Dutch, compared to English, or Chinese for that matter, is really a nano language. So there we go. Technieken om voorwerpen te bouwen uit losse moleculen liggen binnen handbereik. Zo luidde vorige week de openingszin van een interview met Eric Drexler in de Volkskrant. De techniek zelf, hebben we gehoord, heet Atomic Precise Manufacturing. Die zin uit de krant, dus dat technieken om voorwerpen te bouwen uit losse moleculen binnen handbereik liggen, Dat is een zin om eens goed in de mond te nemen, rond te wentelen, te herkauwen en dan door te slikken. Voorwerpen uit losse moleculen. Ik heb nooit anders geweten dan dat voorwerpen per definitie uit moleculen bestaan. Mijn fiets uit ijzer- en rubbermoleculen, mijn huis uit kwartsmoleculen en de vloer uit cellulosemoleculen en uw en mijn lichaam is opgebouwd uit allemaal eiwitmoleculen met wat apatietmoleculen voor de stevigheid. En die moleculen zelf bestaan trouwens uit atomen, die in principe allemaal zo'n kleine 14 miljard jaar oud zijn en nooit vergaan, maar eindeloos worden hergebruikt. Alles is opgebouwd uit de atomen die na de oerknal zijn gevormd. De sterren en de planeten, de continenten en de oceanen, de planten en de dieren, dit gebouw, deze microfoon hier, deze spreker en u allen. Alles bestaat uit een samenraapsel van koolstof, waterstof, zuurstof, silicium, ijzer, fosfor en nog een stuk of 100 andere elementen in afnemende mate van frequentie en hoeveelheid. Maar wel in een uiterst precieze samenstelling. Een beetje te veel magnesium of een beetje te weinig fosfor en je hebt iets heel anders. Iets onbedoelds of ongewensts of onbruikbaars. Maar nog wel altijd iets. Al het iets in het onmetelijke heelal is ooit een keer ontstaan als gevolg van doelloze processen met onvoorspelbare resultaten langs de wegen die door lieden als Newton en Darwin zijn beschreven. Als het mogelijk zou zijn geweest om kort na de oerknal iemand te vragen hoe de toestand er 1 miljard jaar later zou uitzien, zou een volstrekt vraagteken het antwoord zijn geweest. Geen eencellige in de Precambrische zee had kunnen voorspellen dat er een tijdje later trilobieten zouden zijn. Geen trilobiet had de dinosaurus kunnen voorzien en zelfs de meest intelligente dino had geen idee dat er ooit een meteoriet op zijn kop zou vallen. Newton kon de Joint Strike Fighter niet voorspellen. En toen ik zelf in 1983, een tijd geleden alweer, mijn proefschrift uittikte op een elektrische Adler schrijfmachine met carbonlint en een flesje Tipex, had nog helemaal niemand enig idee van de dingen die er slechts 30 jaar later zouden zijn. De Apple, Word en Excel, de laserprinter, InDesign en Quark Express, GPS, Facebook, Twitter en Skype. Deze woorden alleen al hadden in 1983 achter elkaar uitgesproken zoals ik zojuist deed, vermoedelijk geleid tot een spoedopname in een psychogeriatrische kliniek. Nu is het allemaal doodgewoon. Hoe kan dat allemaal? Dat kan door een eeuwenoude verworvenheid die volledig bestaat uit netjes gerangschikte atomen, samengesteld in de vorm van macromoleculen zoals eiwitten en vetten, waartussen nanostroompulsjes heen en weer schieten als knikkers in een flipperkast. Wij noemen dit apparaat het menselijk brein. Het menselijk brein is het hoogst bereikte stadium, tot nu toe althans, op het gebied van atomic precise manufacturing. Het is de meest geavanceerde machinerie om andere machinerieën mee te ontwerpen en te produceren. Op zijn beurt wordt deze machinerie zelf ook weer op de lopende band gezet in een montagehal die we de baarmoeder noemen. En opgebouwd uit, u raadt het al, losse moleculen die uit het voedsel worden gehaald en aan de hand van een nanotechnologisch hoogstandje dat we onze genen noemen. En ook die genen zijn nano. En opgebouwd uit, u raadt het al, losse moleculen DNA en gebruikmakend van allerlei andere losse moleculen zoals eiwitten, RNA, aminozuren, die zelf ook weer uit atomen bestaan. Hoe nano wil je het allemaal hebben? Al sinds het ontstaan van de allereerste levensvorm uit eenvoudige aminozuren, vetten en suikers is atomic precise manufacturing het alles overheersende principe. Met, helaas moet ik zeggen, 7 miljard atomically en anatomically precise gemanufactuurde exemplaren van Homo sapiens als voorlopig eindresultaat. Wat de toekomst zal brengen is even ongewis als altijd. Maar de techniek om voorwerpen te bouwen uit losse moleculen ligt niet alleen binnen handbereik, zoals de Volkskrant wist te melden. Nee, die techniek is al een jaar of 3 miljard met veel succes in gebruik. Opdat u dat weet. Dank u wel.
Jelle Reumer. En ik zou zeggen, ik schrijf nog eens een eerste zin op. Ja, oké. Goed. Well, thank you again, Eric Drexler. We'll be having our next meeting next month, of course. The Knowledge Café will be back. And we'll be talking about education, about learning to learn. We'll have some other guests, I don't know who yet, I guess. Where's Katelijne? We don't have any names, no? But we all like to learn, don't we? Okay. Well, thank you for being here. The bar is open. Eric Drexler is very willing to sign his book. So have fun. Thank you.